Right, it is time. So I'm gonna get started here. Are there any questions from you guys about the set theory stuff that we have talked about up to this point? Yeah.
Well, no, our only thing is just application use. That's about it.
Okay. Did anyone read a little bit ahead of me, like finish the entire document of basic set theory and at least get started on basic quantifiers? Okay, very good. Okay, that's
basic quantifier couldn't open on my computer last night.
Huh?
It didn't open on my computer last night.
It did not open on your computer. So instead of opening, what did your computer do?
Oh no, all it did was just didn't even highlight the languages. It was just like clicking on text name But then when I refreshed it this morning, it was working.
It should be working.
It's not your fault. It was
okay.
My fault.
Okay.
The computer was being weird. It's not you.
All right.
Yeah.
All right. So we're gonna finish the rest of this particular document because we are not quite done with the whole thing yet. So I can show you where we are at this point. We definitely talked about membership, and we talked about how a set can also be an element of another set. Okay, so that's what we talked about. This one here, okay, section number 5 talks about, yep.
Are you recording?
That's a good way to check. Thank you. All right, so.
You should get extra credit.
No, because that does not reflect academic performance.
What's extra credit?
Huh?
You're like, what's extra credit? What is that thing?
There's no such thing in this class.
Yeah, well, say that.
Okay, so I'm watching this right now, and I think the audio is on.
What would you think would qualify for extra credit if you were to give it?
An entire program that allows him to not be here in class.
Like teaching the class for me? Nah. Okay, so let me see why it is there's no sound. Okay, it says headphone is plugged in, but it's not. Oh, that's muted. That's why. Okay, we should be. Okay, it should be playing, but I cannot hear a single thing. There's a little whisper, right? Yeah. Yeah, that's what the previous professor said. Is the audio of these things is set up to kind of like really soft. So I suppose there's a volume control here. Yeah, even with that, it's just a whisper. But it's okay because I can see from the bar here that it's actually playing. So I know the audio part is still good. Okay, I'm gonna close this because it's not needed. So what I did was I was just double checking that the streaming is on and we are actually recording. Yep. Oh, is it hissing right now?
I can hear it, but I can't.
All the way down. There we go. Okay. All right. So section number 5 talks about what do we do when we know a particular set has an infinite number of elements. In other words, what if we want to have a set of all the even numbers? Okay. You cannot enumerate. You cannot list all the even numbers because there's an infinite number of those. So what you can do is kind of like, well, maybe we can just do it this way. Dot, okay, there are stuff before this. And then -4, -2, 0, 2, 4, and then dot again. But that notation is very vague, right? It kind of just tells you that -4, -2, 0, 2, and 4 are definitely members of this particular set. But it doesn't really say, oh, but is there a boundary at the very end of the negative side? Is there a boundary on the positive side of thing? And it doesn't even tell you whether we are only dealing with powers of 2 or not, right? Well, I guess not because 1 should be here and 1. But it doesn't say anything. It doesn't say enough. It's kind of vague. And we don't like things that are vague in this class. So instead of doing it this way, which is typically what people would do when they try to indicate E is a set of all the even numbers. So instead of doing that, I'm going to do it this way. Okay, so we'll focus on this part that is currently highlighted and figure out, okay, what is it saying? So literally what it is saying is E is a set, okay, such that for each member X of E, X has to be an element of Z, which is a symbol for all integers, and X mod 2 has to be 0. Okay, so instead of listing or enumerating elements inside the set, I'm now describing membership of this particular set. What qualifies to become a member in this set, and vice versa. Okay, if you pull something out of this set, what can I say about that one element that I'm pulling out of this set?
Involves equation. Just as an equation or just a description?
It is an expression that has to be true in order for X to be in the set. So instead of highlighting the entire thing, let's highlight just the portion that is important, which is this part here. This is a condition. It's an expression. It is a Boolean expression. In other words, this can be true, it can be false, right? If you plug X equals to 1 into this whole thing, it is false. If you plug in 2.2, this whole thing is false too. But if you plug in 4, it's going to be true. Yep.
Just real quick, I wrote it down, but I can't find it. What does the E mean again?
The E?
Like between the X and the Z?
Just
X and Z. That is element of. Yeah, so you can either use the long way, which is is an element of, or you can just say in. So in this case, it says X in Z, okay? But Z written in this kind of funny way means the set of all integers, which basically means X has to be an integer and X mod 2 has to be 0. Now,
And so that Z means all integers?
Z is the set of all integers. Yep.
Line is means such that.
Yeah, the bar typically is interpreted as such that.
Okay. Wait. The bar that right before the X is what?
Such that.
Such that? How you spell it?
S-U-C-H, such.
Oh,
that.
such. Okay.
Sorry.
Yeah. I thought it was a new lingo. I was about to say, oh my goodness, man. I'm gonna jump off the roof.
Well, it's called Chinglish.
Oh, okay.
See, only I can say that. You guys say that. All right. So is that okay so far? Every element in this particular set X, X can be an element of this particular set, or every element in this set X has to make the following condition true. Okay, and the condition is just this part here. Okay, this is the part of the condition that has to be true for every element in E. Okay, now we can make something that is totally senseless. Okay, so I'll show you what is senseless in this case. Let me get my stylus so I can write on my tablet. There we go. Okay. Yep.
So is X then an element of Z and an element of E then?
Yes. So every element in E is automatically an element of Z. Because that's a requirement. Because of this requirement here. So we know that every element in E has to be an element of Z. Which later on, that particular relationship has a name, but we'll talk about that later. So right now I need to fire up my tablet. So let's see. And we'll try to refresh. Nope, it needs to be restarted. Okay, that's fine. Okay. There we go. Okay. So let me give you an example of a particular set that doesn't seem to make any sense, but it is still okay. from the perspective that we're still describing a set. But you guys will have to tell me what is in this particular set. Okay. So I say X is a set. Okay. The curly braces are important, and I'm going to use this notation. Every element X in this particular set has to meet the following criteria. Okay. So I'm going to say X is how about this? Backspace. There we go. X is less than 0, and X is greater than 0. Okay. So what do you think? Okay, I'm going to add one more thing because, okay. Let me back up a little bit. If this is this is the way I describe X, then what can possibly be in X?
Empty zero.
Well, it can't be zero.
It can be from 1 to.
It can be non-numbers.
Exactly. Because X doesn't have to be a number. I didn't say that X has to be a number, right? So I can be in this set because I'm neither less than 0 nor greater than 0.
So you just be random integers.
It can be no, not integers. Every integer
Not
is a
integers,
number,
I mean,
and integers have.
variables.
Yeah, so it can be anything other than numbers because you cannot compare non-numbers to 0. It doesn't make any sense. Does
So
that
it
make-
could be alpha, beta, A, B, C, whatever.
Yeah, because the attack is less than 0 is not true.
Okay.
Okay. So that's why, if I want to make the point that I really wanted to make, I have to add one more thing. I have to say that X is a real number.
And that symbol there is real.
Yeah, that's a real number symbol. It's an R that has, that's kind of funny with an R. Yep.
I'm not understanding why you have to say that X is a real number. Because anything that isn't a number just would.
What about a complex number?
Well, I think aren't there not complex numbers that are less than and greater than zero?
But you cannot compare a complex number to a single 0.
Yes, it'd still be false. It's not a reasonable thing to compare anyway.
Right, but it's not less than 0. That's the whole point, is it is not less than 0.
Yeah, so it'd still be an empty set. Right?
That would be kind of interesting because we have to find out, okay, do we consider a non-real numbers, anything that is not a real number, can we say something about it? Is it less than 0 or greater than 0? But this makes more sense to me now, because now that we are restricting X to be a real number, we know for sure that the comparison has to work. Yep.
This might be a game question, but would a set count as not a number, or are sets in a different category by themselves?
A set is not a number.
Okay, so it's either number or not.
Yep. But the bottom line, that I really want to illustrate here is X is an empty set. There's no such real number that can be both less than 0 and greater than 0 at the same time.
Okay. So if it sounds impossible, then the answer might be impossible.
Well, you have to evaluate it on a case-by-case basis. Yep.
So in the context of sets, do we always view a 0 as a numerical value?
Mm-hmm. Oh, yeah, I guess, sometimes I use it to mean false, right?
Yeah.
Yep. But when we use the less than symbol, then we're comparing things that are comparable. Booleans technically are not comparable. Like true is not greater than false, okay? But in C, I'm not sure about C++, but in C they are comparable because in C, not C++, there's no such thing as a Boolean.
That's news.
All right. I'm going to have to send some of you guys back to CISP 360. What is considered false in C++? Do they have a word false?
No.
In C,
Oh,
regular.
I thought you said C++, my bad.
Okay, in regular C, do they
Okay.
have false?
No.
No. So what is considered false? 0. Okay, but 0 can be a null pointer, can be the null character, can be 0 as an integer, can be 0 as a floating point number. They are all false. Then what is true? Anything other than 0.
Okay.
Okay, 1 is true, 5 is true, -5 is true. this pointer that's pointing to that object somewhere in memory is true. Is that okay? Can we compare 5 versus 0? Is one greater than the other one? Yes. So that means in C, true and false can be compared. Okay? Even though it doesn't seem to make any sense. But in mathematics, it makes no sense to compare true versus false. Yep.
Do you have a particular symbol that we use for the empty set?
Hmm?
Or do you have a particular symbol that you want us to use for empty set?
I'm just going to use this one, open and close curly brace. The other symbol, which is kind of like a circle with a stroke through, is a little bit too ambiguous because sometimes I write zeros like that too. So I just don't want to, use that one.
So just the two squirrely braces just mean empty set?
Yep, nothing in between, right? You're looking at a box that has no content inside. Is that okay? All right, cool. All right, so switching back to the notes again, okay? So in general, what we are doing is we are describing a set using this notation. So basically, we are choosing a way to represent an element inside the set. So at this point, we're just going to use a particular variable, a name, like x, y, z, whatever, to describe, okay, let's pick one thing in the set, we'll call it x here, so that we can refer to that element later. So the purpose of x is to give a name to whatever element we decide to look at that is inside the set. And then P is a predicate, and what a predicate is basically it's just a function that returns either true or false. Okay? It can be a very complicated equation, can be very simple, we don't really care. Okay? We just know that P is a function that returns true or false. And it takes one parameter. So every element in X has to make P return true. That's the notation that we are using here. So in the example right here, all we are doing is to say, oh, P of X is defined as X is in integers and X mod 2 has to be a 0. Okay, so P of X is really just a predicate. It is some expression that has to evaluate to either true or false. Is that okay? So it's just an abstraction. It's a method to describe something. Is that okay? Yep.
How would you, at least in that format where it's E is equal to X, if PX, how would you show what P was alongside it?
You can define it on the side. In other words, if you you can do something like this. You can say X equals to X such that P of X is true. So if I don't say P of X equals true, that means implicitly I'm looking for the conditions when P is true.
Right.
Okay, so then you can define P of X separately.
Is equal to and then
Yeah.
with brackets and
So we can to make this match the example that we have seen in the notes. So now we can just say that X is an element of the set of all integers, and X mod 2 is 0. I'm just getting lazy, so I use the %.
Can you go back over this part one more time?
You basically say, okay, this is uppercase X is the name of the set.
Right.
But what is in the set? Well, whatever X that makes P of X true.
Oh.
Then you go like, okay, then what is P of X? Well, P of X is defined to be this conjunction. X is in Z, which is the set of all integers, and X mod 2 is 0, which basically means X is even. Go ahead.
You said you got lazy with the mod. Is there another way to express the mod?
Spell it out, MOD.
Yes, no.
Yep.
All right.
Which is still an abbreviation because the full name is modulus.
Modulo.
Yep, modulus. But in C and C++, the percent symbol means exactly that, which is the remainder of a division.
And so all we're saying is that the element of X is just X such that for P, and then that's
every element of uppercase X has to make P of X true. And P of X is defined da 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 da. Okay? So there's another way to look at this. Okay? Whenever we use this particular form to define a particular set E, it really means exactly the same thing as this statement here. So this statement, what is that saying? Okay, let's spell out what this statement is saying. It says X is in E if and only if P of X is true. Well, but wait, this is important because it's a double-sided arrow. So that means whatever makes P of X is true, that X belongs in E. But it also says the opposite. If you take any element out of E, oh, I know this guy is in E, take it out, it has to make P of X true. So it has to go in both directions. If you find something, a particular value, K, okay, P of K is false, what do you know for sure? It is not in E in this case. Okay? If you know a particular thing, let's say, M is not in E, what do you know? P of M is false. So that is important because it's a double-sided arrow, if and only if. So are we okay so far with all this? Okay. All right, so the rest is really, saying the same thing. So I'm gonna skip reading all that part. Section 6 is really simple. We encountered this already. A set that has no element is called, guess what? The empty set. But it's still okay. It's kind of like a folder that has no file in it. Okay, it is still a folder, except there's nothing in it. Is it useful? Is an empty set useful in any particular way? It is very useful. Okay, so we'll see. Okay, at the end of this entire semester, we'll be talking about the Dijkstra's algorithm and/or the A-star algorithm. And in both of those algorithms, we'll start to use the set notation, and you will see how the empty set is useful in those algorithms. All right, section number 7 is kind of long because it talks about all the set operators that are fairly useful. The first one is the intersection of two sets. So A intersecting with B is a set itself, but what about this new set? Well, I'm using this notation. See, we are making use of something that we just talked about. So the set that is the result of the intersection of AB is a set, but what is in this particular set? Let's read this one here. Every element E in the intersection has to meet this requirement. What is that requirement saying? At the same time. So E has to be found in A and found in B at the same time. If it's only found in one of the sets, it won't be in the intersection. Is that okay? All right, so intersection is done, but it also means the same thing. If E is in the intersection of AB, that means it is if and only if A is in A and E is in A and E is in B. It means exactly the same thing.
There can be more than one, right?
Huh?
There can be more than one.
Yes. So what this is really saying is, if for any element in E, for any element E in the intersection, that other condition has to be true, and vice versa.
Right.
Because we haven't really talked about quantifiers yet, so we cannot say for all. But your point is well taken. There can be more than one element that meets this requirement, or none, for that matter. Yep. What about union? So A union B is a set itself. Well, as a set, it has elements. So what about the membership of those elements? An element E is in the union of AB if and only if the element is found in A or the element is found in B. It doesn't have to be found in both. It can be one, it just has to be in at least one of the two. Yep.
So
So intersection is sort of like an and union is sort of like an or.
Yes. And you might notice that the symbols are also kind of like that too. Because union looks kind of like a rounded version of or, and an intersection looks kind of like the rounded version of and. Are we still doing okay so far? Cool.
Might have to do some outside research, but we good.
Okay, well, we'll use some examples after we introduce some of these concepts. So the next one is quote-unquote subtraction, but it's not really subtraction. It is we borrow the subtraction symbol here, but it's not exactly subtraction. Okay, so let's find out what this one is. Okay, A minus B is a set. So once again, we have to talk about membership. Okay, what is in the set of A minus B, or the difference between A and B. So any element E in A minus B has to meet this requirement. It has to be found in A, but not found in B. So everything that is unique to A is in A minus B. Anything unique to A when you're only considering A and B is found in A minus B. So are we still doing okay so far?
Yeah, so that's like kind of like exclusive just to A. So that's exclusive.
Exactly. So relative to A and B, A minus B is a set with elements that are exclusive to A. That is one good way to put it too. Yes.
What is this operator called? What is this operator called?
Difference.
So if
It's-
there's a single intersection, it means that's no longer true.
Say that one more time.
If there's a single intersection, that means this is no longer true. Like
If there's an intersection, that means A minus B is not going to be just A. Okay, so let's play with some examples and see what happens. Okay, so because examples are always useful in this case. So I'm going to define two particular sets. I'm going to define T for tack, right? To be the cars that I like. So we're going to say MR2,
Ooh,
MX5,
ooh.
and
2JZ, 2JZ.
You know,
what is the Honda NSX?
NSX.
Yep,
Honda's NSX.
it's a Honda. NSX, that's the mid-engine, right? They have a new version of that too.
Yeah, it's in
Yep.
the new tier.
So we'll use uppercase G for George. Okay? George likes the NSX 750 BMW
Oh,
and Odyssey.
the Odyssey. The heck?
Well, George is a family man.
Oh, okay, my bad, George.
A very responsible family man. I'm one too, but I'm not that responsible. If I have to take my kids to school, I have to make 2 rounds.
There you
I
go.
have
That's
2
a fast
kids.
car. So
Huh?
you can make those 2 rounds quicker.
or I would just say make them both just wake up early and
Or one in the
go
trunk.
places.
One in the trunk.
That's true.
What trunk?
Drive fast.
What trunk are you talking about? Stacking. Okay, so with these as the 2 sets, okay, what is T blah 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 G? Okay, I'm not gonna spell the term out. Yep, because it is what is common, right? So it's just NSX. What about T blah 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 G?
All of them.
Okay, now, okay, but when you say all of them,
Except
tell me what it is. Okay, tell me how you would describe the content of this set. Go ahead, one by one. MR2, MX5.
NSX only once, write that twice.
Aha! Good job. Okay, so NSX only appears once because each unique element can only appear in a set up to once. Okay, very good. So then we have 750 and the Odyssey. Audi. I think I'm pretty sure I misspelled Odyssey, but close enough. Why would they choose a term that's difficult to spell?
Oh, it's
The
a
name
please
is
to
hard.
the American market, because when Honda gets together, they say, how can we sell this to Westerners? Oh, give it a Greek name.
I believe it.
Now, I used to design video games, and that's when we use all the meetings where, how do we appeal to the Western artists? Give him a Western name. Okay, we call him
It's a
Western.
real engine.
There you go.
What about T minus G? The difference.
AMR2 and MX5.
Exactly. So the intersection should not appear here. So that would just be MR2 and MX5 because NXX is common. Is that okay?
Wait a minute.
What about the rest of it?
Because T minus G would be everything in T but not in G. Okay? MR2 is in T but not in G. Cool. MX5 is in T but not in G. Cool. NSX, hey, is here too. So we do not include it in T minus G.
And then if it was reverse, and then it would be
750 Odyssey.
yeah. So if it was reverse, then it'd be those. Yeah.
So G minus T reversed is going to be 750 and Odyssey. And trust me, the 750 is a long car. George actually at one point he was he asked me to store his 750 in my garage, and it barely fit, widthwise and lengthwise. And I couldn't even put that thing to reverse because it has that the BMW iDrive kind of digital control thing. I drive a stick shift, like a mechanical stick shift. When I look at an electronic thing, go like, ew. What do I do with this?
Willkommen in Deutsche Autos, yeah.
What is that?
Oh, welcome to German automobiles or German cars.
Okay. Danke.
Yeah.
Okay, so are we okay with these concepts? Intersection, union, difference. Is that sufficiently illustrating those concepts?
Yes,
Clear?
clear, yeah.
Okay, excellent. Because I want to make sure that those concepts are clear before we move on to more operators. So the next one is kind of interesting. The next one is called the Cartesian product, which is represent Cartesian product. Okay, Cartesian product. Okay, and the Cartesian product is really interesting because it's kind of like a generator. Okay, so let's take a look at the definition of the Cartesian product. A Cartesian product B is what? Well, the result is a set. How do I know the result is a set? Open curly brace, close curly brace indicates that it is a set. What is in the set? This is the time when we go like, hey, how come we are not using a single letter to describe an element? Instead, I'm using paren x comma y close paren. That is called a tuple. In fact, this is called a two-tuple because the tuple has got two things in it. So a set is a container. A tuple is also a container, but there are major differences. In a set, the order does not really matter, right? If I list, MX5 ahead of MR2, when I list the content of T, it's just as good. Okay, there's no difference if I change the order of the listing. When you're dealing with a tuple, order is important. Okay? And the second thing about a tuple is they can be the same. X and Y can be exactly the same thing. It's perfectly okay. It's just like an array. In other words, if you think about tuples, think arrays because they are pretty much the same thing. It's just that one is a mathematical term, the other one is a programming term, but they're pretty much the same thing. Are we doing okay so far? Okay? So this is basically saying everything inside the Cartesian product of two sets is a tuple. And this is a two-tuple, so it's got two components. The first component, I just call it X. The second component, I'll call it Y. So now the question is, are there restrictions on X and Y? Yep. X has to be coming from A, which is the set to the left-hand side of the operator, and then y has to be from B, which is to the right-hand side of the operator. Is that okay? In other words, if you're given a vector or an array for one set A and then given a vector for the other one, this is generating a matrix, a table. And then each item in the table would have two items. Okay. So just to continue with our example, let's see what happens when we cross T and G. So, okay. This is the furthest I can scroll up, but that's going to be okay. So when we look at T cross G, we know the result is a set. But what is in the set? Well, first of all, how many elements are you expecting in that particular set?
2, 3, 3.
No. Yep, go ahead.
Can you have like different like types in an array or non-array in a tuple?
The concept of a set or tuple has no type restriction.
Okay.
So you can put anything into a particular set, unless you have the unless you describe and you say, oh, everything in this set has to be blah blah blah.
Yeah.
But without that, there's no restriction whatsoever. Okay, so how many things are in this particular set? There are 3 items in T and 3 items in G. So, okay, I'll give you guys a few choices. 0, because 3 minus 3 is 0. 3 itself, because 3 equals 3 equals 3. 6, because 3 plus 3 is 6. 9, because 3 times 3 is 9. Or 27, because 3 to the power of 3 is 27.
Oh my goodness. That was all 3.
Oh, right. 3 divided by 3 is 1. Okay, so there's one more choice. The correct answer is 9. Because for every single element in T, I can pair it up with any element in G. For another element in T, I can pair it with any element in G, and so on. So if I want to enumerate this particular set, it's going to be pretty long because there are 9 items, and each item is a 2 tuple. Okay, so I'll give you a few, just to start with. So we have MR2 paired up with 750. Okay, round parentheses. Okay, got to use the right kind of parentheses. MR2 can also pair up with NSX. But this NSX is not from T. This NSX is from G. The second component is always coming from the set to the right-hand side of the operator. Okay? And then we got one more, which is MR2 paired up with the Odyssey. Okay? The next row, let's pick on MX5. So MX5, same thing, can pair up with 750. MX5 can pair up with NSX. And MX5 can also pair up with the Odyssey.
Is there a reason why you're starting with the 750, or?
No particular reason.
Okay, just as long as the T's on the left and the G's
Yep,
on the right.
because ordering is not important. Now, ordering is important inside the 2 tuple, but between the tuples, it doesn't make any difference. Okay? In other words, if you look at the tuples as individual things, okay, I can reorder the tuple any way I want inside the Cartesian product because the Cartesian product itself is a set. And each tuple is an element in the set. And all those elements can be reordered, the way I listed. It doesn't make any difference because it is a set. So the last row is kind of boring in a way because we got NSX paired with 750, NSX paired with NSX itself. It is perfectly okay because this is a 2 tuple. The first NSX comes from T, the second NSX comes from G. Okay, so that's important because we are not dealing with a set. The 2 tuple itself is an element in the set, but the 2 tuple itself is not a set. Okay, and the last one is just NSX, Odyssey, and oops, I put this too early here. Now we have an end curly brace because this end curly brace is ending the set that is the Cartesian product. Yep.
I have a question. So this is the 2 tuple. What if what is the 1
Just the tuple itself.
Say that one more time.
What is just a tuple on its own?
A tuple on its own?
Yeah, just not a tuple.
A single tuple, a singleton tuple. You will still use the parentheses, and then you have one single item in it. So you can have a tuple that is empty. You can have a tuple that has a single item, but in this case, because we're using the Cartesian product, it has to be a tuple that has two items. So are we doing okay so far?
Yeah.
Sure.
Let me finish taking the notes first before you.
Okay.
Oh, come on, man.
You can take a picture too. I don't mind, as long as I'm not in the picture.
Recorded, it's online.
It's online, exactly.
Oh no, I got it now. I just memorized it
Okay.
at the last minute.
Question?
What if you were to multiply a set like this with another set like that?
With what?
With another set like that.
With
I mean, like another set containing double tuples. You would have 81.
that is a good question. It depends on the context in this case. So basically, you're asking, can tuples nest?
Yeah.
Yep. It really depends on the context. When we get to that point, we'll talk about it.
Alright.
Yep. Because it does complicate things a little bit here.
Yeah, I would imagine.
All right. Let's check something out here. Okay, so let's check out this particular example. And you guys will tell me what it is. What is that? T the same way the same way it was defined as before. So T is not an empty set itself. It has got the MX5, the MR2, and the NSX. Okay, but I'm looking at a Cartesian product.
So the right side will be empty from all of the parentheses.
Okay, so let's do something that is for sure. We know it is a set, don't we? The Cartesian product between two sets is always a set itself. Is an empty set a set?
Yes.
Come on, the name does. It's an empty set. Of course, it is a set. So now we have to look into the definition of the Cartesian product, right? Every two tuple inside the Cartesian product has two components because it's a two tuple. The first item has to come from T in this case. The second item has to come from the empty set. Does the empty set have any elements? No. So that means the Cartesian product between these two is an empty set. There's nothing in it. So I was definitely misleading you guys into thinking that there's something in this Cartesian product. There's nothing.
So does it matter if T has anything in it?
Does not matter at all.
So like multiplying by 0.
Huh?
It's like multiplying by 0.
In a way, yes.
So if we put 0 in the bracket, there would it be wrong?
If you put a 0 inside here,
Yes.
that would be wrong because now you're saying the number, the digit, not a digit, but the value 0 is in the set, which it is not.
Okay, so just leave it like that.
Exactly. Well, not without all its spaces. Yeah, there was another hand earlier.
Just wait, somebody asked a question.
Oh, okay. Okay. So is that addressed there? Okay. Okay. So are we doing okay so far with Cartesian product?
It just it would I just have one more quick question because I noticed that we only have MR2, MX5, and NSX, right? And I was just wondering, is it like the way that we get there? Are we taking one from each and then comparing it to the one on the bottom? So we're just saying that we get the 3 cars on the top and then we write them in there 9 times and comparing it to the
There's no comparing. There's just pairing.
pairing. Yes.
Yeah.
T by G, so you don't want to take what's in T and match it to itself.
Right.
So it's whatever T has paired with one of whatever G has.
There you go. Thank you.
Yeah, but the pairing doesn't have to be between different sets. In other words, I can do something like this. This is totally valid.
Right, but it wasn't specified in that one.
That is correct. Yeah. So the example, did not specify that we are crossing with T. We're crossing with G. That was what the example was.
Is
All
there
right.
any value to doing Cartesian products with?
Itself?
Yeah.
Yes.
No. Okay.
So we'll be using Cartesian products a lot in this class. Okay. So when we start to talk about functions, We'll talk about this. Yep.
Let's say we have like two sets, like A is 1 and 2,
Okay.
and then B is 2 and 3,
Okay.
and we cross them.
Yep.
Would you get 3 things or 4 things? Because like there's 2 parentheses, 2 comma 2s in there.
Okay, so we are looking at 1, 2,
Yeah.
crossing with 2, 3. Okay, so remember the
Just 2 times.
requirement or the membership definition of the Cartesian product. Each element is a two-tuple, where the first one comes from the set to the left, the second one comes from the set to the right, right? Okay, so we'll systematically look at all of those elements here, okay? So we'll first consider all the two tuples where the first, where we are using one from the set to the left, okay? What can that pair up with? You can pair with 2, but it can also pair with 3. Whoops. Okay. Then we consider the other element in, yeah, so I think you just answered your own question, right?
No, I had something. Okay, never mind. I think I just messed up when I was doing it. Because when I was doing it, I guess I messed up and had like 2 2 2s. So I was wondering like, wouldn't they?
Ah.
Yeah, but.
Okay.
So it wouldn't actually be possible to get different elements from the Cartesian.
That is correct. You end up with a lot more elements than you started off with the only exception of you're dealing with a set that only has one element or at the empty set. Yep.
So that second set, then instead of 2 3, that was 2 1,
Uh-huh.
right? And you still, I guess, if you were to write them out,
Well, let's
like
find
you,
out.
like you, yeah.
If this is a 1, you just change all the 3's to 1s.
Oh. And then so I'm guessing if you vice versa. Oh, never mind. I was gonna say if you vice versa.
Yeah.
Is that making any sense?
Yeah.
Yeah, because we are just really taking every element from the first one and pair it up with every element on the other one. Yep.
I think I got confused, but I thought sets weren't really concerned about the order, and therefore you couldn't have a set that was 1 2 and then another set that was 2 and 1, because they'd be considered the same.
Yeah, but these are not sets. 1 2 is a two-tuple. 2 1 is a two-tuple.
But you're using sets to make the tuples, right?
Yes. But 1 2 as a two-tuple is considered distinct or different from the two-tuple of 2 1.
I think what he's asking is those two sets,
The sets
the
they're actually
original
putting
sets
in.
are the same,
That's
so
what
it's
I'm
the
concerned
same thing. Like it's a set A and set A.
Is that T by T then?
Yeah.
No.
So the 1
You can
2
do that.
2 1.
Why not? I mean, the two sets to the two sides of the Cartesian product can be the same. In fact, most of the time, it's going to be the same when we talk about functions.
So you can do like set A, set A.
Yeah. And it happens a lot. Okay, that was a good question, but the answer is yes, you can have a Cartesian product of a set with itself.
And those 2 tuples inside, even if they might be identical to another 2 tuple that's inside, they're considered different elements.
As long as the ordering is different. So order is important. In other words, in this case, 2 2 can only appear once.
Right.
Okay? But 1 2 is considered different from 2 1 because the 2 tuple 1 2, even though it has the same values as the 2 tuple 2 1, the ordering of the values are different. And that's why they're considered different.
Could you just do a Cartesian product on this a set
And then
with
2
itself
1
with
2
itself?
2.
Yeah, sure. I mean, this is, with the red correction, that is a set, the Cartesian product of a set in itself, because the set 1 2 is technically the same as the set 2 1.
Right.
Yep.
But as long as you have just a difference.
Well, I mean, the ordering doesn't change anything because inside a set, the ordering has no significance. Is that okay? No? Okay, what is not okay?
Well, I'm not understanding how we're gonna do. It's two different three sets in this case, right? The first guy said one and two set and three set. That's what multiplying three sets.
The result of the Cartesian product is a set. Yes.
Yeah, but I'm talking about this is three sets multiplied. One in another, one in another, and that's another.
You can do that, but then we get into the question that was asked a little bit earlier, which is basically, do we have nested tuples or do we just make a tuple longer? And I'm not going to answer the question at this point because it depends on the context. Sometimes it makes sense to have nested tuples, and other times it makes sense to kind of concatenate and just make a tuple longer.
Okay, so I'm confused. This one, which one is exactly it? This one and this one.
There's no problem here. That problem only exists if I say cross with something else here. But since we only have one single Cartesian product, it's okay, because one comes from this one comes from the first set. This two comes from the second set. They make a tuple.
Okay, it makes perfect sense, but I was confused with that. I thought you were doing that example. Doing it too.
It is kind of important that we get this down because it's a self-contained topic. In other words, even though some aspect of this, will be discussed later, the core, should be understood at this point. The definition of what is a Cartesian product, what is a tuple, how is it different from a set, those concepts really need to be cleared up at this point.
You said that tuple can have more than one element, right? Or, I mean, more than two elements.
What can have more than two elements? Yeah, you can have a 3 tuple, a 4 tuple, and so on. So are we doing okay, or are there questions about these concepts?
I'm glad you stayed there because I forgot that you have to count declaring the rows as how many is in each of the element. Yeah, I didn't even realize that until right now.
Oh.
Yeah. So yeah.
Could you do like a 3 tuple?
Huh?
Could you do like a 3 tuple?
No, because if I do a 3 tuple, okay, so to make a 3 tuple, I can just draw make one like 1, 2, 3. That's a 3 tuple. But I'm not saying where it comes from, right?
Oh, I mean, as far as like I was asking if you could just like do the Cartesian product of 3 to get.
Not yet. Not yet, because in order to end up with a 3 tuple, you need to apply Cartesian product twice.
Right.
But I'm not ready to talk about, should that be nested or should we just be extending a tuple to be longer? Because there are two ways to interpret that. Yep.
Are there infinite tuples just like there's infinite sets?
In theory, yes, but in this class we do not encounter those. Yep.
Oh no.
Oh, okay. So any other questions related to Cartesian product? Nope. Okay. If there are no questions about this, then we'll go ahead and look at this statement here. Okay. So we are talking about subset at this point. Now, let's focus on something that we already know. So forget about the subset notation and focus on the part that is currently highlighted. A minus B is an empty set. In other words, we do not find anything that is only in A but not in B. That is the definition of A being a subset of B.
Did you read that? Does that make it say A equal B, or E does make it E equal B, or E contained in B?
All it says is A is a subset of B. A is a subset of B if and only if you cannot find anything that is in A but not in B. Which is also the same thing as saying everything in A is in B.
Oh. So it's contained in B.
So So it can't
No,
have anything.
well, I wouldn't. I mean, that's not what I said, right? What I said was A is a subset of B, if and only if everything in A is also in B. But I did not specifically and carefully. I did not say that B contains A, because containment is a little bit more ambiguous than subset of. Okay. Yep.
But you could say B contains all elements.
Same.
Yeah, but it has more elements besides A.
That is correct. B contains all elements of A is still a proper way to describe it. Yes. Yep.
So just for example's sake, an element that's I mean, two sets that satisfy this condition is, for example, A is 1, 2, B is 1, 2, 3, 4.
Mm-hmm.
Okay.
So then one becomes the subset of the other. Okay, that was a hand. Yep, go ahead.
So B can be more than just the elements of A, right?
Yes, B can contain elements that are not found in A. That is correct.
But it'll still be a subset of A. Will still be a
A
subset.
will still be considered a subset
So
of
if
B.
if you have like A that has 1, 2, B can have 1, 2, 3. Right?
Yep. Mm-hmm.
So if B contained A, but like if B had A as an element, but it didn't have all the elements.
I wouldn't
of A,
use the word contain, okay? Because when you use the word contain, because in the physical world, in order for a container to contain something else, the one being contained is always smaller physically. But when we are talking about subset of, that is not the case. In other words, the set 1, 2 is a subset of the set 1, 2. That's perfectly okay. Yep.
So if B had A as an element, not using the word contain. If B had A as an element, but it did not have all the elements of A, we would say that A is not a subset of B.
I'm laughing in that particular way because what you said has to do with element of, which is kind of independent to what we are talking about here. All right, so let's use your example. Okay, so I'm gonna define a. Okay, let's pick a different color. What?
You got the switch.
Oh,
You would've
okay.
just been writing.
Okay, thank you. Well, thank you for letting me know. Okay, so we'll just define A to be, say, 1, 2. Okay, is that okay? So what you said was B, A is in B. A is an element of B.
Like the elements of A are not separate from A.
So okay. So in that case, B obviously can have things other than 1, 2, right? So I'll just say 3. Okay, but it also has A, which is a set of 1, 2. Right? So in this case, the question now is one of these two sets, okay? Is A a subset of B, or is B a subset of A, or it's like, what are you talking about?
Technically, it should not, because A, the subset of A, it's not included in A itself.
Yep, exactly. So what is A minus B? Okay, tell me what is in this particular set here.
It's 1, 2.
What is in A but not in B? Okay, 1 is an element of A, but is 1 in B? No. So you're right. So both 1, 2 are in A minus B. What about the other way around? What is B minus A?
Will be subset of 3 and
3
1, 2.
and the set of 1, 2. In other words, B minus A is B itself. A minus B is A itself. Right? None of those two is an empty set. So that's why A is not a subset of B. B is not a subset of A. They're just not subsets of each other. Yep.
Is it possible for two sets with the same things, like so say A and B have the same thing but they're just named differently? Is that possible, or do we just automatically rename it to A? Like say A has 1, 2 and B has 2, 1. Or whatever.
When you decide membership, you have to look at the definition. So the name is really just a macro, it's just a name,
Right,
just a symbolic name. So it doesn't really impact how we compare. Okay? So in this case here, what we can say is A is a subset of B is false. B is a subset of A is also false. They are not subsets of each other.
Okay.
Okay?
So that line indicates that it's false, yeah?
Hmm?
So when you say that A is not a subset of B and B is not a subset of A, when you have the C, that operator there with the line under it, that just indicates that that is false, that the mod is in between A and B.
This is just an operator. In other
Yeah.
words, it is just saying, it's a question.
Yeah.
Is A a subset of B? Okay, when you see the operator, it is just asking, is A a subset of B? So the answer can be true or false, right? So in order to make sense of what we just talked about, I have to say, well, if A and B are defined this way, then A is a subset of B is false. That expression returns false. B is a subset of A as an expression is also going to return false because they do not, one is not, a subset of the other. Is that okay? Yep, go ahead.
So just to recap, when it says A is a subset of B, that means all elements in A are also found in B, but
Yep.
B can have elements that are not found in A.
Say that last part one more time.
All elements in A are also found in B, but
Yep.
B can have elements that are not found in A.
That is correct. B can have something that is unique to it. That's fine. Okay, so let me give you another one. What is A minus A?
Empty set.
A minus A is guaranteed to be an empty set. Okay. What does that automatically translate to in terms of subset of?
A is a subset of A.
Yep, every set is a subset of itself. Wait, there's that special subset, or there's that special set of empty set. Is the empty set a subset of itself? Does it meet the requirement?
Yes.
Yep. So the empty set turns out to be a subset of itself, and equivalence? What means equivalence?
Both sets are the same.
Well, A is always equivalent to itself. Okay, so that's good. But focusing back on the empty set. Okay, so I just said that the empty set is its own subset, right? But there's a greater truth related to subsets and the subset and subset of. The empty set is also okay, think about this. Okay, here is my empty set. Here is some unknown set X here. What is found in the empty set that is not found in X? Nothing, right? Okay, so by the very definition of the empty set, an empty set minus whatever set X is always an empty set. How does that translate to subset of? Exactly, the empty set is a subset of every set. Is that okay? So are we sufficiently confused?
Not yet.
Not yet. Okay, we'll throw in the next one, which is going to make things more confusing. Okay, so are we ready to switch back to the notes?
Sure.
Okay. So the next one, the next symbol or next operator that we want to define is X is a proper subset. So without the little bar underneath, it is now called proper. Okay. So X is a proper subset of B if and only if da 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 da. Okay. So what is in the da 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 da? Okay. So what is that saying? A is a subset of B. Okay. We know that because we just talked about it. And B minus A is not empty.
But you said that names can't match essentially, right?
What?
That these are different names, but you're saying it's the same set, right? That it can't be the same set.
A and B cannot possibly be the same if B minus A is non-empty. Because B minus A being non-empty means there's something in B that is not in A. That is the definition of a proper subset.
What does that mean?
Huh? it means A is a subset of B, and there's something in B that is not found in A. In other words, very vaguely, B is bigger. Now that is, I put it in quotes because bigger is really hard to define. Okay, so think about this. We'll revisit this again later on. Think of the set of all natural numbers. Okay, and when I grew up, natural numbers is 0, 1, 2, it includes 0. Okay? Now think about the set of all even numbers. 0, 2, 4, 6, 8, and so on. Okay? Both of these are big, right? They're infinitely large. There's an infinite number of members in each of these sets, right? And you can definitely say that, hey, one has elements that is not found in the other one, right? Because one is in the set of all natural numbers, but one is not found in the set of all even numbers. So you can definitely say that the set of even numbers is a subset, proper subset of the set of all natural numbers. Does that make sense? Perfect? Cool? But is it really big? Can you say that the set of all natural numbers is bigger than the set of all even numbers?
Because they're both.
Yeah, everything is not is positive. Yes.
But it can.
Can you say one is bigger than the other one when they are both infinitely large? In this case, as it turns out, you cannot. These two sets are actually quote unquote, they have the same, well, okay, I'm gonna scroll here. They have the same cardinality. Dun dun dun. Okay? Cardinality is basically counting the number of members inside a particular set. So the cardinality of T is 3. The cardinality of G is also 3. The cardinality of the empty set is 0. Very good. Okay, what about the cardinality of all natural numbers? Infinite. No. If it were just infinite, that would be easy. But it's not. Because you cannot compare infinite with infinite. Okay? So later in this class, in this semester, we'll actually look into the cardinality of the set of all natural numbers versus the set of all even numbers versus the set of all integers versus the set of all coordinates, okay, all integer coordinates in a 2D, two-dimensional plane versus the cardinality of all 3D coordinates, but each coordinate is an integer. And guess what? They are all the same.
Are you talking about because limited by the number of, like limited by the computer or limited by?
Nope. This is purely from the mathematical perspective, okay? But it's related to computer science. Okay, so you're going to say the cardinality of integers is the same as the cardinality of natural numbers. It is the same as the cardinality of 2D coordinates, okay? As long as the coordinates are using only integers, which is the same as the cardinality of all the 3D coordinates, and so on. They are all considered the same. So I'm not gonna, yeah, go ahead.
Is it like when you're referring to cardinality, sometimes like an example would be like how to count the indices of numbers?
Well, when you compare the cardinality between two sets, each one has an infinite number of members, then the only way you can compare is to say, is there a way for me to map, okay, for each element of this set here, I have a way to map it to the other set, and vice versa. For every element on this set here, I have a way to map it to a unique element on this side. If you can find a mapping that can go in both directions, then the two sets will be claimed to have the same cardinality. Okay, so we'll talk about that later because we need to talk about functions, injections, rejection, and that sort of thing before we can make that make sense. But for now, we'll just I'm just planting the seed in your head and go like, the cardinality is a little bit more tricky when we talk about the set of integers, the set of even numbers, odd numbers, and stuff like that. Yes?
So in the example you have down below, it
Uh-huh.
has the two lines on the side of the sets.
Yes, they're just vertical bars.
Yeah.
So the vertical bar
does that
versus
mean that's
cardinality of, yep. Which is basically the same thing as length of or size of, in C and C++. Yep.
So cardinality gets complicated when a set is infinite.
When a set has an infinite number of members. Yep. Now, when you compare the set of all real numbers versus the set of all natural numbers, then we can compare. Okay? Because there's no mapping that can go in both directions. So they are definitely different. Okay? I'm not going to say which one is bigger, but they are different. So we are done with this slide. Are we good so far?
Okay, good. I was just wondering if you do an example
Of
like how before it come out to 2 or 6 and 8.
It's just counting how many elements do we have in a set.
Oh.
Because that's exactly what we are saying. Many times we are interested in the number of elements in a particular set. The notation bar x bar is called the cardinality of x. So that's why it is important to read ahead of me, because a lot of times the details is kind of, some of this is easy, it's just by definition. Yep.
Okay, so from my understanding, the difference between a proper subset and a subset is the subset by itself as definition, it might be equal.
Yes.
But
And hence the bar. Yep.
Yeah, proper subset is not equal for sure.
They cannot be the same, correct. Yep. It's just like less than versus less than or equal to.
Yeah.
Okay? Yep. It is analogous to less than versus less than or equal to. All right. So I'm gonna leave this one and say that it's okay for now. If you guys have any questions about it, we can go back and talk about it. But if not, we're going to talk about quantifiers. So quantifiers are really important, in our discussion, because sometimes we have to differentiate between, are we talking about just one of these things? Are we talking about all of these things? Or are we talking about at least one of these things, right? Okay. So what we want to do, is we can talk about the basics, and whatnot, but we can talk about, just, casual, conversations, sentences that you use on a daily basis, and see how we use quantifiers on a daily basis. Because if I cannot connect the concept to something that you use on a daily basis, you're not clicking, you're not making the connections, right? Okay. So let me make a statement. It can be true, it can be false, but I just want you to focus on the meaning of the statement. Okay? Every professor knows what he or she is talking about. It's a statement. How is that different from there's at least one professor who knows what he or she is talking about?
Not every professor knows what he or she is talking about.
Okay? Okay, so you're getting it, right? So if we qualify ARC using one of these two statements, from the perspective of the president of this particular community college, which one do you think that president wants to choose? The first or the second?
The first.
The first, because the first basically asserts that every single professor on this campus, all, I think several hundreds of us, knows what he or she is talking about. What about the second statement?
Chance of it might be false.
No,
There's a
no. The
chance
second
that-
one states, at least one professor on campus, at ARC knows what he or she is talking about.
More it could mean literally just the one.
Exactly. It only assures you that one of the many professors knows what he or she is talking about. Cool. Question?
Oh no, don't try to crack
Oh.
my neck, man. We got
Oh, okay.
that neck.
Okay. Because of this class.
No.
Okay. So, that's. Are you guys getting that concept? Okay. How do we say there's no professor at ARC who knows what he or she is talking about? But but you have to use negation, and one of those things that we just talked about earlier.
The negation of
professors know what they're talking
everything
about.
encompassing.
So
It does exist.
Okay, so you start with it is not the case that, okay? But which one are you going to choose? Okay, let me give you the two options. Are you going to say it is not the case that every professor at ARC knows what he or she is talking about? Or are you going to say it is not the case that at least one professor knows what he or she is talking about? Which one equals exactly the same as saying no professor at ARC knows what he or she is talking about? Second one. Think about it. It is not the case that every professor at ARC knows what he or she is talking about. Oh, that means Tech may know what he is actually talking about. It leaves that possibility, right? But the second one, which is saying that it is not the case that at least one professor knows what he or she is talking about at ARC, we're just saying, oh, that leaves us with no one. Not even one.
No one or more, maybe.
Hmm?
It can be.
At least one, not at least one.
So it might be none or everyone.
No, it can be a negative number, but not.
Whoa, wait, what?
Okay, so
So the first case says not all of them, and the second case not one of them.
okay, so let's use x to represent it. Okay, x is the cardinality. See, here cardinality comes in handy. And we'll use lowercase p to represent, a. Oh, okay. Okay, there we go. So we're gonna use this notation. Okay, we're reusing everything that we have talked about. The set notation, the bar thing for cardinality and stuff like that. So x is defined to be the cardinality of a set. What set are we talking about? Okay, for every element p in this particular set. Okay, p is in. Okay. How about that? I'm just going to use a symbol to represent profs at ARC. Okay? I don't really care about CRC, SCC, or FLC. You guys can come to your own conclusion. Okay? And P knows what P is talking about. Okay. Okay, so obviously not very mathematical, but you get the idea. Is that okay?
So what was the first one again?
And then we have one bar at the very end because we are trying to figure out what is the number, right? What is the number of professors at ARC who knows what he or she is talking about? Right? Okay. So if we say at least one professor knows what he or she is talking about, what are we talking about x?
It's greater than 0.
Greater than 0 or greater than or equal to 1. The same thing because we cannot have a half professor. Is that okay? So this means at least one blah blah blah. Okay, at least one professor at ARC knows what he or she is talking about. Is that okay? What about, so I'm going to reverse the question. What if I want to say no profs at ARC knows what he or she is talking about? Then x is, well, technically less than or equal to 0. Right? But if x is less than or equal to 0, it's also the same thing as saying it is not the case that x is greater than or equal to 1. Which also means the negation of at least one professor at ARC knows what he or she is talking about is exactly saying no professor at ARC knows what he or she is talking about. Does that make any sense? Sort of? Okay. What if I want to say not every professor at ARC knows what he or she is talking about? It is the negation of. Exactly. It is the negation of every professor at ARC knows what he or she is talking about. Is that okay? So it looks like we really get the concept of quantifiers. It's just that we don't refer to those things as quantifiers. Every time, ironically, every time we say every, it's a quantifier. Every time we say each, it's sort of a quantifier. Okay? Every time we say some, it is also a quantifier. Every time we say none or no, it is a quantifier, or the negation of a quantifier. If I say there's no vacant parking space anymore, okay, which happens a lot, right? So you guys are very familiar with quantifiers. You use it every single day, every morning, followed by a few cuss words, right? Or preceded by a few cuss words. Okay. So when you say there's no parking space left in the parking lot, how do you convert it into the quantifiers that we talked about? At least one versus every, and then using negation. It is not the case that there's at least one vacant parking spot. That is the same thing as saying there's no parking spots. Right? So think about this and read this document because it is really important. And when you're done reading this one, because we have a kind of like an interval of 5 days, that we don't meet. When you're done with that, I want you to move on, to talk to the next one, okay? To set theory using quantifiers.
That's homework, son?
The homework is not on yet, okay? So, so right now the assignment is still reading. But as you're reading, don't just read, okay? Memorization is not going to get you anywhere in this class. So every time you read, you kind of think about the meaning, okay? If you think you're confused, okay? What is a confusion, by the way? What is the definition of a confusion?
Something that is chaos that you cannot comprehend.
No, that's not comprehending is not confusion. Confusion is there are several ways to interpret something. There are several ways to say, okay, does it mean this A, this B, or this C? That is a confusion. Okay? Not understanding something is different. Okay? Not understanding something means there are no alternatives to choose from. It's an empty set. You're choosing from an empty set. That is not understanding. But when there are alternatives in the set, when the understanding is a set that has more than one element, it's a confusion because you know only one of those things is true. But which one is it? That is a confusion. So when you have a confusion, ask questions. Okay? Give me the alternative ways of interpreting something, and I will help you clarify which one is the actual text. Okay? I know you guys have to move on, so I'll see you guys on Monday. Have a nice weekend.
Have a nice weekend.